We looked at very simple functions previously. Now we're going to take a broader look at function definitions. Function definitions allow you to specify both positional parameters, which are the kinds of parameters that we specified in the past. Argument values when you call a function are matched up with these positional parameters from left to right, one by one. Python functions also support something called keyword parameters. For each keyword parameter, you specify a default value that keyword parameter will take on if the user who calls the function does not specify a value for that keyword parameter. A keyword parameter definition looks like a variable name and then an equal sign and then a default value. Notice that all of the positional parameters, if the function has any, have to come ahead of all of the keyword parameters, if the function has any. Keyword parameter might be a somewhat unfortunate name for these. The names of keyword parameters are not like Python language keywords like if and else and while and for. The name of each keyword parameter simply has to be a valid variable name that's different from the names of all of the other parameters for this particular function that you're defining. So you use def to define a function, as we've seen. You specify the name that you want the function to have, and then in parentheses you give as many positional parameters as your function is going to require, followed by any keyword parameters for which you want to specify default values. Then we have our good old colon out at the end. Following that, we can specify a string in a pair of single quotes or a pair of double quotes, or more commonly a pair of triple single or triple double quotes that specifies documentation for how the function is to be called, what the meanings of the parameters are, and what the function returns. Below the docstring, if the docstring is given, we have a sequence of one or more statements, as we've seen. So here on this slide, we have a function called printpow, which has both a positional parameter called x and a keyword parameter called y. Now, y has a default value of 2. What this function does, as this docstring says, is to display the value of the first parameter taken to the power of the second parameter. Therefore, if the user calls printpow with only one argument, the squared value of that is going to be displayed. Let me hammer in this function definition and then call printpow with 5. And we see that printpow computes and displays the value 25. If I call printpow with 2 arguments, 5 and 3, let's say, then printpow computes and displays 125. You may have seen this little flicker of documentation appear when I type printpow and hit the parenthesis character. Most development environments, and in this case the interactive shell for idle, will display the parameter names for the function as well as the docstring. Now you can't see the docstring here because my window is a little too tall for that. Let me shrink my window height a little bit, and then you'll be able to see the documentation displayed. Okay, so here we can see that the parameters are displayed and we get the docstring, display x to the y power. So let's try 6 to the 4th, 1296. Now, optionally, you can treat a positional parameter as though it were a keyword parameter by specifying its name when you call the function. So I can say printpow x gets -7. Y will have its default value of 2, and the result here is going to be 49, of course. If I specify the names for all the parameters, I can even change the orders of these things. So if I say printpow of y gets 3, x gets 2, this is going to compute 2 cubed, which is 8. However, when you call the function, you must specify all of the positional arguments ahead of the keyword arguments unless you specify names. So if I say print pow y gets 4, 5, Python doesn't understand that, well, the 5 doesn't have a name, so it should be attached to the first positional parameter. I just get yelled at here. Positional argument follows a keyword argument. The print function is a function that has keyword parameters that we haven't talked about. If I say print 1, 2, 3, by default, I will get a space as the separator character between the string representations of these 3 int values. 1 space 2 space 3. But I can use the sep keyword argument to specify a different separator. If I say print 1, 2, 3, sep gets comma, and I have to represent comma as a string here, then my output's going to be 1, 2, 3. The print function automatically adds a new line character to the end of the output. The keyword parameter for that is called end. I can specify a different end if I prefer. So I can say print 1, 2, 3, sep gets an empty string. Okay, so I want no separation between the values. And the end here is going to be an exclamation mark rather than new line. Okay, now you may have noticed a brief little hiccup there at the end of that output line. You probably didn't notice. The reason that the prompt is coming out on a separate line from that output is that the shell itself will add a new line if it discovers that output was produced and no new line was displayed. So in this case, the print function is not generating the new line character. The shell is generating its own new line character to cause the prompt to come out on the next line down. Every function returns a value, specifically returns an object, or a reference to an object, to be really precise. You can either use a return statement with some expression to create the object to return. If you don't have a return statement, either intentionally or because you forgot, which unfortunately is common, what you get back from the function is none. So here on this slide, I'm defining a function called oops with one positional parameter x. If the value of that parameter is greater than 0, I'm going to return x minus the value of that parameter. And that's the conclusion of my function definition. Obviously, I forgot to have an else part with a different kind of return. If I say a gets oops of 5, now 5 is greater than 0, so this is going to compute 5 minus 3 is 2, and return to me a 2. Therefore, a, if I display a with print, displays as a 2. But if I say b gets oops of minus 7, which is less than or equal to 0, the if test fails, and I get a default return. And the default return value is none. So you can make use of this intentionally, or you will get it by accident if you mess up the logic of your function and don't have a proper return from all the possible threads of execution of your function. Variables and their values are kept track of in something called a symbol table. A symbol table is simply a dictionary, a dict, that maps from the variable name, which is stored as a string in the symbol table, to the value associated with that symbol, with that variable name. I can use the function globals to display the dictionary of the global variables that my shell is aware of. Many of these are variables that the shell sets up for itself. These are not variables that we created. For example, there's a special variable __name __ that provides the name of the currently executing module. Here, because I'm interacting directly with the shell, the value of that __ name variable is __ main __. We also have special variables named, I won't keep saying __ over and over again, but we have variables named doc and package and loader and spec and so on. We also have a built-in module of built-in functions like print, like len, and so on. And here, toward the end of the symbol table, recall that the items in a dictionary are in the order in which the keys were created. Here is my printPow function that I defined, as well as my oops function that I defined, and a couple of global variables, A and B, that were created to store the return values coming back from oops. Okay, so these are all of the top level or so-called global variables that my shell is aware of. There's also, for each function, something called a local symbol table for that function. And I can see it by using the built-in function locals. Now, in the case of the shell itself, the variables that are local to the shell are the same ones that are global within the shell. But if I call a function and examine the local variables within the function, it will be a different, smaller dictionary from the globals. So every time a function is called, a brand new symbol table is created for that function's execution. And what's in that symbol table are the parameters and other local variables that that function uses internally. Here I have a function f1 that I'm defining, f1, that has two positional parameters, a and b, as well as a keyword parameter, c, whose default value is going to be high. And in the body of this function, I'm going to print the dictionary representing the local variables that were created for this function call. All right, so I'll print that dictionary, locals, and then I'm going to print the values of the objects referred to by these variables A, B, C, and D. And that's it. So that's the definition of F1. Now, if we take a look at that definition again, notice I'm printing A, B, C, and D. A and B are the two positional parameter values that are local within the function F1. They're not the same as the global A and B that I already created. C here is the keyword parameter, whose default value is high. D I have not specified as a parameter, and I have not assigned a value to D inside of F1. So if I were to run F1 right now, this would actually fail. Let me do that right now. Let me say F1, 1, 2, 3. Okay, so the F1 function is able to take 3 argument values. The first one will be assigned to A, so A will get 1, B will get 2, C will get 3. It will not be high. But there is no variable existing currently that's named D, so I'm going to get an error message. Okay, the local variables within the execution of F1 have A referring to 1, B referring to 2, C referring to 3, but there's no D, so I get an error. However, it turns out that if you try to access a variable inside of a function that is not a local variable within the function will then test to see whether that variable is a global variable. So now I have created a global variable named D I can see that it's global by asking for to see the globals, right? And I now see that I do have D created as a global variable with a value of 22.22. And now if I run F1, this time let me run it with 2 and 3. Therefore, A will get the value 2, B will get the value 3, C will have its default value of high, D, since it's not a local variable, will be treated as a reference to the global variable D. And so what I end up displaying are the local variables inside this execution of F1. A is 2, B is 3, C is high. And then I get the values for A, B, C, and D displayed, 2, 3, high, and 22.22. I want to point out that now that I'm back in the shell, if I look at the globals, the global variable A still has the value 2 that it had way back here from the return value of oops 5. It's a little bit of an unfortunate coincidence that it happens to be the same value that I passed to F1 here. But notice that the value B is still none that I got back from the oops function when I passed in a -7 as an argument. All right, so this F1 function has its own local variables A and B, which are separate from the global variables A and B. Okay, so functions are our first level of abstraction in programming and provide the basis for what's called top-down programming or functional decomposition. For example, we start out with some complicated problem that we have to solve, and it's not immediately obvious how to do that, but we just take on faith that we can write a function that's going to solve our problem for us. Okay, so we write down this outline for this topmost function. And regardless of how complicated the problem is, we can usually break that down into a brief sequence of simpler steps. We can say, well, in order to solve this big complicated problem, I know that I'm going to have to accomplish these 5 steps. Okay, and then once again, we sort of take on faith that each one of these simpler steps can be implemented as a function. And within each one of those steps, we can break things down into yet smaller steps. Eventually, we will break things down to such a level that we get down to functions that have trivial and obvious implementations. As we get down in this hierarchy of functions, we may discover that we need to sort of back up and tinker with some things at higher levels, but eventually we'll get everything broken down into some appropriate hierarchy of functions that solves our original problem. For small to medium-sized programs that are very computation-oriented, this is actually quite a useful approach and was more or less how programs are written through the 1980s or so. As memory became cheaper and processors became faster, computers branched out to things that were not just traditional computations, and keeping track of huge amounts of data in flexible and efficient and safe ways became more important. And so object orientation, that is the idea of defining your own data types that help you solve your problem, became the second important leap forward in abstraction. But even in object orientation, the implementations of the individual method functions that operate on the data at the lowest level often involve shallow hierarchies of top-down programming using functions. It will sometimes happen as you're doing this decomposition of your problem into smaller steps that one of the steps in a solution will just be a smaller version of the same problem that you started with. It turns out this is not a problem. You can simply have the function that you're writing call itself to solve that smaller identical problem. This is an example of recursion. Now, because each time you call a function in Python, you get a brand new symbol table containing copies of that current function call's own parameters and local variables, recursion is supported in Python. That is, each call's local variables, including parameter variables, are separate from any other function calls local variables and parameters. As an example, let's take a look at starting with a string and creating the reverse of a string. Now, a list has a reverse method that we can call, but a stir is immutable, and there is no reverse method that we can call for a stir. So in order to get the reverse of a string, we have to build a new string object, and we want the new string object to have the same characters but in the opposite order as the characters in the original string. One way we can certainly do that is to use iteration on our string. Here I have a function named Revster it, so reverse string iteratively. What we're going to do here is to start out with a variable for the string that we want to return. Initially, the string we want to return is empty. And even though a string is immutable, we can seem to be modifying this returned string by using our +gets operation to concatenate a string onto the end of the existing return string and then update that return variable to refer to that new concatenated strings. All right, now we need to count backwards, and we know that we can use the range function to count backwards if we need to. And in fact, indexing in a sequence makes this quite convenient, because we know the last item in the string is going to be item sub -1. We will count downwards, so our step is also -1. And after a moment of thought, we will know that we have counted down one too far if we reach the length of the string +1 in a negative direction. Let's remember why that's true. -1 is the last item in the string, minus the length of the string would be the initial item in the string, and so minus the length of the string +1 would be one step too far. When we're done with the for loop, we then return this ret string. Now, obviously we can't do exhaustive testing of every single possible string that we might ever pass to Revster it, but we should always check certain edge cases or boundary cases. For example, our function would definitely better work if we pass in an empty string, and we see here that it does. In fact, let me type this thing in so that we can confirm it's working. I'm going to define Revster it and now we'll call Revster it with an empty string. That succeeds. We should also test whether Revster it works with a string that's just one character wide, and it does. And those are actually the two most difficult cases to get right. So if we've tested those, other things will probably work okay. And let's check Revster it of hello world. And indeed we get, well, obviously I can't pronounce that. We get it in reverse. Okay. Now, so that works. It's not extremely difficult, but the algorithm is kind of a mess. You do have to stare at it a bit. You do have to persuade yourself that the end of the loop is going to be at this, or one before this, minus len s plus 1. A recursive implementation can actually be easier to understand. Here is our Revster recursive version. Within the recursive implementation, we first test whether the length of the string that we're reversing is 0. If the length of the string that we're reversing is 0, then we just return an empty string and we're done. Otherwise, if the length is not 0, what do we know? Well, we know that we want the endmost character to come first and the other characters to come afterward. So the endmost character in S is S sub minus 1. That character needs to come first, and then the remaining characters in the string come afterward. Well, the remaining characters in the string are the slice S sub colon minus 1. That is, all of the characters in S up to but not including the last character. And we have this function that we've just conveniently written called Revster Recursive that can give us recursively the reverse of a string. All right, so let me type this guy in, def Revster Recursive. Okay, so I've finally gotten this thing successfully typed in. In my first attempt, I forgot the colon after else, which, despite how long I've been doing this, I still forget that colon after else frequently. This is also a good illustration of why I really ought to be doing this in a code file rather than interactively. But in any case, I've got it typed in, so let's test it now. Revster recursive of an empty string works correctly. Revster recursive of A works correctly. Revster recursive of hello world also works correctly. Okay, so again, if we look at the iterative solution, we have to scratch our heads and think a little bit to persuade ourselves that this really ought to work. The recursive version, once you're comfortable with the idea of recursion, is some ways more straightforward to understand. We first test whether the string doesn't have any characters, and if not, we just return an empty character. But if the string does have characters, we return the last one, followed by the reverse of the preceding ones. And because each invocation of this revster recursive function is going to have its own private copy of S, separate from all the other functions parameters named S, this will work. In fact, notice that this first thing that the recursive function does is to test whether there's nothing to do in some sense. That is, to test for and do nothing if the task that it's been asked to perform is the so-called empty task. Now, in this particular case, it's not quite the empty task, but if there are no characters in the string, then we return an empty string and we're done. This is called the stopping condition for the recursive function. So, in order to conclude, a recursive function has to test for and stop when a stopping condition is reached. Secondly, of course, the original task has to be finite. If we had an infinite string, then this recursion would never stop, and of course that would be a problem, although of course that would also be a problem for our iterative implementation. The third thing that's necessary in order for recursion to work is that each subtask that you break your original problem into has to be discretely simpler than the original task. Let me show you an example where the subtask is not definitely simpler to show you a recursive function that definitely will not work. If I say revster rec2 s, well, okay, have to say define. So if I define revster rec2 of s, okay, let's see what's happening here. So I want revster recursive 2 to return to me a reversed copy of S. Oh, let me think now. I have this revster rec2 function that returns a reversed copy of S. So let me just return revster rec2 of s, and I'm done. Well, actually, no, I'm not done, for two reasons. First of all, I have not broken the original problem down into two discretely smaller subtasks. I have my task, which is to reverse the string, but then my subtask is the same string, not a smaller string. And the second but related problem here is that I'm not checking for any stopping condition. So this function is written recursively. It is a recursive function, but it will never complete. It will run until Python cannot allocate symbol tables anymore, at which point it will crash. Okay, so in order for a recursive function to work, we have to test for a stopping condition and do the appropriate trivial thing when we encounter the stopping condition. The problem that the function is solving has to be a finite problem, and the subtasks being solved within the implementation have to be discretely simpler than the original task. All three of these things have to be true in order for a recursive function to succeed. Now, reversing a string is a fairly trivial thing to do with a recursive algorithm, and the recursive algorithm is not really that much simpler than the iterative algorithm. But if you're dealing with so-called linked data structures, which we will in Financial Computing 1, such as binary trees, linked lists or doubly linked lists, general graphs of nodes connected by arcs, then recursive algorithms often turn out to be quite easy for navigating your way through these linked data structures, and equivalent iterative algorithms may be very difficult to write. So recursion needs to be a very natural part of your toolkit and needs to be as easy for you as iteration. There are many mathematical functions that are often defined recursively. For example, previously we implemented a factorial function using iteration in a for loop. But often a mathematical definition for n factorial will be specified using something called a recurrence relation like this. 0 factorial is defined to be 1, and then for any integer greater than 0, we define n factorial to be n times n minus 1 factorial. Okay, so 0 factorial equaling 1 is the stopping condition. For any integer n is, of course, finite. And in order to compute n factorial, we're breaking that problem down into two discretely smaller subproblems. We know how to multiply by n, and recursively, we can compute n minus 1 factorial since we know that we will eventually hit our stopping condition. So here on this next slide is the Python recursive implementation of the factorial function. Define fact recursive for n. If n is less than or equal to 0, we're going to return 1. Now, in fact, we'll consider negative values of n to be errors, although we're not going to complain about that. If we do happen to get past an integer that's less than 0, we're just going to return a 1. Otherwise, n must be greater than 0. So we're going to return n times the factorial, recursively, of n minus 1. All right? So that is really the mathematical definition of recursion this way, implemented very simply in Python code. We can compute the factorial recursively of 3, and we know that's 3 times 2 times 1 is 6. We can compute the factorial recursively of 100, Well, we don't know what that is off the top of our head probably, but there is the result. Now, it turns out that Python does have a ceiling on the depth of recursion that you can do, because Python does have to be able to generate a symbol table for every recursive call of this function. And that's not free, that does take memory. And so by trying to compute the factorial of 1000 recursively, we do bump up against this implementation's ceiling on recursion. So that is a potential real-life problem with recursion that is a greater concern in Python than it would be in a language like C++ or Java that are more stingy with the memory that they allocate. Recursion can be difficult to get a handle on at first. In fact, there's a joke of sorts, not necessarily a good joke, that in order to understand recursion, you must first understand recursion. Now, basically, recursion is what I call a light bulb experience. You either get it or you don't get it. There's no sort of halfway. You simply need to make yourself write recursive functions to solve problems enough times until suddenly it will all make sense to you. This will become more clear when we do start taking a look at linked data structures where recursive algorithms are often natural and obvious, and iterative equivalent algorithms may be very difficult to come up with.